Okay, the first talk is for the SIBYLL by Felix. Okay, we can start.
Oh, okay, that's it. Thank you. Um, yeah, so the slides are only a couple of hours old, so at some places I'm not so sure what's in there myself. Um, what I need to say, why is this? Okay, so this, okay. Um, so I mixed up the thing on the Indico. So I'm not at Lib anymore. I'm at ICFI in Santiago. First thing. Okay, so I'll talk about SIBYLL. And okay, of course, thank you for the invitation, but I see the main organizer didn't seem to have made it yet. Okay, anyway, I'll get started so that we don't get too delayed. So I'll start with the airshow development. So we've seen this already, just so that I can get ease into the talk. I need this. So okay, when our hadron comes in, there will be a first interaction, which is if it's a proton or nucleus QCD. And then the main feature that you have here is that you produce well, hadrons, and neutral pions will decay into photons. And then there's some other hadrons that also do that, but most of them is neutral pions. And then there's the other group of hadrons, charged pions, kaons, nucleons that that also decay the pions, but only after when they're at low energies, right? Okay, and so what happens next is that all these particles can interact, and then you have the same QCD interaction again, and the same thing happens. And then on the other side, the photons, they will make a electromagnetic cascade, and then uh, not produce hadrons, at least not very frequently. Okay. Um, and that means that of the primary energy that comes in, it's immediately split into these two channels, the electromagnetic cascade, which then goes on, and then the hadronic, and the energy transfer is always from the hadronic side to the electromagnetic side. And so roughly this looks like this, the energy balance. So in blue is the hadrons that will interact again, producing hadrons, and in red is the pi zeros basically. So the electromagnetic energy, which is just about 15, okay, here it's 16%, but let's say so at this level. And then 80%, or let's be generous, 20%, and then 80% goes into hadrons that interact. And then if this goes on and on, very quickly, most of the energy is in the electromagnetic cascade. Um, okay, and then of course the muons that are produced from the decay of the pions, and I have this here, right? So in basic shower observables that you have is like the particles at the ground and the shower development, so the maximum, and you see here the electromagnetic cascade is much more numerous. So what you see is the electromagnetic cascade in X max. And as I've shown before, so the more largest chunk of energy comes in the first interaction into the electromagnetic cascade, right? So they're basically decoupling in the first interaction already, and so X max is influenced by the position of the first interaction and how much energy you get into photons there. Whereas for the muons, they are produced in the decay of charged pions mostly, which is at the end of the cascade, right? So when so you're depending on the full chain of the hadronic interactions, and that is basically where the problem comes from. Okay, now cut SIBYLL, I think. Yes, exactly. Um, so I'll not tell you in detail what goes into the model. You can, if you are very interested, you can look into these two publications. Um, but just in basic terms, so of course the protons here, this black ring here is composed of partons or quarks and gluons in the model, and then there's we construct a probability distribution for how how many of these scatterings you have when the two hadrons meet, right? How many of the partons, quarks, and gluons interact with each other? Um, and yeah, the details are in these papers. And then what then this leads to configurations that you see here on the right, right? So you had your proton, it has some valence quarks, and then there's interactions maybe between some number of gluons. In this case, it's like it's one, and so they exchange color, and then you get that's these dashed lines here, representing the color fields, which then turn into hadrons, right? And so basically the model generates different configurations of this, which then turn into hadrons, and then you have the time state. Okay, very basic. Now the muon discrepancy in SIBYLL 2.1 is quite significant, right? You see here, this is the usual figure that we've seen before, muon content on the side, X max on this at some fixed energy. This is in the Auger measurement. And then you see that with SIBYLL 2.1, you would think that the data should be somewhere here, which is really far away. So that was the job a while ago. How do we fix this? And so these are the two of these mechanisms we've also already seen during this week. We used in order to improve this in SIBYLL 2.1. So on the left here is that Ralph introduced this already very nicely, right? So if you produce more baryons, so protons, antiprotons, and so on, they very clearly they keep the energy in the hadronic cascade, right? Because baryon number is conserved, so they will propagate until they're basically at rest and can produce particles all the way until to that point. Okay, in the center here, sorry, let's skip first to the other side. So in strangeness, it's basically the same thing, at least at high energies, right? Because QCD conserves strangeness, and so unless the kaons, unless they decay, which they decay via the weak interaction, so they will stay kaons, and then if you have a kaon interacting, it will not produce, or is less likely to produce a high energy neutral pion because strangeness is conserved. And then the energy also stays in the hadronic cascade. So it's very similar to this baryon conservation. And then only when the energy of the kaons is low enough that they can decay, then this mechanism stops. And then in the center here, this is also what Ralph already showed. Again, with the leading particles, right? If you have a pion and it turns into a leading neutral pion, then you get photons immediately and the energy is lost to produce muons. Okay, so we've seen this already a lot this week. And so now we did basically these two things are underrepresented in SIBYLL 2.1, which is the reason for this low number of muons, right? So here's baryon production. So this is the average number of antiprotons as a function of the center of mass energy. Here in low energy fixed target experiments, and then this is LHC in limited phase space, so CMS mostly. That's why there's two lines, right? So this is full phase space, this is just central rapidity. And so the dashed you see at low energies, maybe this still works okay in SIBYLL 2.1, but then it falls already here below the data, and here it's very much below the data. And so how this is produced in the model is whenever you have these color fields, there's just one parameter which tells you how often you basically make a baryon instead of a meson. But it turns out that it's not as simple as just increasing this rate here, because we were already describing kind of okay the low energy data with SIBYLL 2.1, you couldn't just enhance this everywhere, right? In order to describe these data here, so in other words, would have to make this not universal. However, this was also already observed that the formation of baryons, and I think Peter Skans also mentioned this, that it's I mean, it's not so trivial as this picture of breaking the color field lets you maybe think. And this is an example of studies at low energies of this epsilon resonance, which decays via two gluons and a gamma, and among other channels. And this you can compare to just slightly lower energies where you have just photons interacting in your E plus C minus collider, where this resonance is produced. And then you get a quark anti-quark system, right? And then you can compare the hadron production in these two systems. And what you see is that in these gluon-rich systems, you get more baryons in this case, right? Lambdas, protons, and so on. So there is already some indication that this depends a bit on how the colors are configured between here and here, how we produce baryons. Okay, and so then what we did was we basically we just enhanced the baryon production whenever you have many gluons present, which is supposed to be the case whenever you have many of these additional jets that are shown in the very beginning. Okay, and so yeah, here you can see how this looks like in CMS again. Now this is the ratio of antiprotons versus charged pions. We've seen this yesterday by Tanguy as a function of this number of basically a number of binary collisions in the interaction. And yeah, okay, so 1, and then we go up and it's okay. And well, there's maybe it's not all okay. There's some trends, but at least it's much better in terms of production. Okay, and next topic, which this is beam remnants. So in SIBYLL 2.1, that we didn't have that. All we did was you take a proton that is supposed to interact, and then you split it into these two pieces, one with one quark and one with two. And in any interaction that has a color exchange, this will be then the configuration, right? So in this way you keep the protonness, so the valence quarks are always attached to these strings, and so the quantum numbers are conserved, and then you do manage to describe the things that you want to describe, like if you have a proton-antiproton collision, that afterwards you have more negative particles on one side, on the side where the antiproton came from, and the other way. Okay, so for that it works, but otherwise it's maybe a little bit too limited in this form. And so what we added is the explicit remnants of the beam particles, right? So the proton, we take out the valence quarks and separate them, and these color exchanges are then attached to just some C quarks, so we have additional flavors here. And then the remnant goes into resonances of the proton, right? So here you have a nucleon, the first resonance of protons, and you have the deltas and whatnot. No, sorry, this was the proton. This is the first resonance. Okay, and with this, first of all, it was very nice that we actually also managed to describe the LHCf data better, right? So you see here SIBYLL 2.1, this flat curve. This is the very forward neutron spectra, and then with this remnant treatment, yeah, okay, you get this. At least it's better described. There's of course still some processes maybe missing, possibly pion exchange. Yeah, but it works this way. And then it also gave us the flexibility and at this to fix this problem that we saw in NA22, which is here this forward production of pi zeros versus rho zeros, right? So you see the model SIBYLL 2.1 makes this flat for the pi zeros forward, and then the other one is just a scaled down version. And then now with the remnant, we can explicitly make these rho zeros here, and yeah, describe this very nicely. Okay, so and what did this give us? Okay, so I have here the way we use these two processes. So this is the number of muons relative to SIBYLL 2.1 as a function of the primary energy, and we get with this basically a 40% increase at 10 eV in proton showers, which is very nice. And okay, you see how these here you can also see how these different processes matter. So at so the baryons make more are more consistent in their production of muons, whereas for the rho zeros it's more important to have a longer cascade. Okay. However, this is unfortunately not really enough in order to describe the data, right? So we were here, this is SIBYLL 2.1, and now we're up here with these basically these two processes that were added. There are other things in SIBYLL 2.3D, but these are the main ones that drive this number of muons. And okay, so it's still not enough to get complete consistency between the measurements. So can we enhance this further? And that's why we started to work on what I will talk about next, which is SIBYLL star. Sorry. And but first, another motivation, and I mean we've seen this week also already. So this is the problem with the muon deficit is that we don't have a consistent description of the data, right, that we can trust. So you cannot really train, let's say, this for Auger, machine learning algorithms, for example, to interpret the signal as a function of the time of the shower that is measured to reconstruct things, like in this case, Xmax, right? Because what's found then that this measured Xmax that you get in the hybrid events has a 30-gram bias. So it's very much correlated, but it's offset by 30 grams. And now the question is this because we have too few muons in the simulation, right? And for this, we wanted to make a model that does have sufficient muons, but because it was relatively hard to do this in SIBYLL 2.3D, which was also motivated describing the accelerator data, so we say, okay, we just do this artificially. So we take SIBYLL 2.3D, produce the particles, and afterwards we go through the list of particles that we produced and replace particles according to these mechanisms. So either we produce we replace pairs of pions or triples of pions with protons, antiprotons, or with kaons, or with rho zeros in order to mimic these mechanisms that we had already studied. And we do this with a specific rate, and then we call this event then SIBYLL star. Okay, and so we do this in this following way. So the rate is some basic rate which we want to go to at highest energies, and then we make an energy dependence. So we turn and end the threshold. So we say at DV sorry, at LHC energies we don't want any modification. So this would be 0, and then we maximal modification at the highest energies, or this factor then turns to 1 at 10 eV. I think we did, yes, 10 eV. And then in between you scale it up logarithmically. And then here we have a phase space factor. So either we want to do this, we just want to scale up the spectra as they are in longitudinal phase space, or maybe we want to enhance the forward part or so. Okay, so this is what we use basically, and we did 4 variants. So 2 were motivated, as I said, by SIBYLL 2.3D, right? The success of the spirant production and the rho zero enhancement. Then strangeness enhancement is also very much hot topic in the literature, and of course we've seen this in central collisions in HC. And then okay, we also made a mixed model which takes these 2 together, which means you don't have to be so drastic in each of the components. Okay, so these 4 variants we made, and this is how these parameters were adjusted, right? So and the left is pions, and the center is antiprotons, and the right is strangeness. And so it's basically in the pions you don't see any change here. This is proton-proton interactions for any of the variants. And then so you see the proton variant we built to basically kick in after the LHC energies. So there you see this enhancement. And the same thing for this strangeness enhancement, right? Because we have data here from LHC, we just turn it on afterwards. Okay, and this is going back to the very beginning of the presentation. What matters is the energy in hadrons, right? And this is how actually the parameters then were adjusted. So we give every of these variants the same chance. Sorry, I should say. So this is the energy in the hadronic component with regard to the standard SIBYLL 2.3D, right? So and this is 1, so this means there's more energy in the hadronic component by 10%. So we fix at the highest energies, 10 to the 20 proton showers. All these variants they have the same propensity to produce muons because we fix them to enhance the energy in the same way. And then okay, they go down in different ways because we have less constraints for the rho zeros, right? Okay, and so sorry, this is pion carbon, of course, and proton. Okay, and then yes, it does actually work. So finally, with this, we get sufficient muons. So same figure again. Here's SIBYLL 2.3D. If you do this strangeness enhancement above LHC energies, you make it up to here. Antiprotons slightly bit more. so say efficient in producing muons, which we understand, right? Because they go all the way to low energies, whereas the kaons start decaying at some point. And then rho zeros are, let's say, the most efficient mechanism, and then this mixed model also goes spot on through the data point. And okay, so now this is how it looks like at. So we started at HT energies, which we say is 13 TeV. So that means we have modification at 14 TeV, and this is how it would look like. So this is what you would need to measure in order to test this this modification at the 14 TeV. And you see it's not much, right? So in kaons, you need to measure this. Okay, this is the basically lab energy spectrum. So it's hard to get a detector there, but even if you have one, you need to resolve very small differences. Okay, except for the antiprotons. There you have maybe a good handle. So that's a difficult, gonna be a difficult task. And so what are the predictions for showers? Just one thing is you see here on the left is the energy spectrum. So basically in any of these mechanisms, except for the antibaryons, you scale up the energy spectrum as it is. You get a slightly different slope with the antibaryons because again, they are the ones that go all the way to the lowest energies. And on the right, you see what this effect is on the LDF or the lateral distribution of the muons. And there, okay, also comparing to the other models, and it's really interesting that this doesn't seem to touch the other shape, the other degrees of freedom in the shower development, right? Because you get more muons, but you basically the LDF just goes up and down. And you do still see a difference with, for example, APOSH IRC between all the SIBYLL variants, but among each other, they're the same. So this shape seems to come from not just the pure number of muons. So this makes it now very interesting, and I'm sorry, I cannot tell you what the result is going to be. What this does then if you do detailed analysis in Auger, say, or TA or wherever, and in particular if these machine learning things, if you can use this model and you get you get rid of this bias that I showed at the beginning. And okay, yeah, so this is already my summary. Okay, I talked about baryon production, row production, and SIBYLL 2.3D. And just as an introduction, more or less, a very long one, to then talk about the SIBYLL star variants that give you sufficient muon production. And the mixed model is actually the one that we gave to the people that work with the machine learning in Auger, for example, which they then call SIBYLL star, and then we'll see if that fixes things. And yeah, if you want this model, I can give it to you, no problem. Just let me know. Okay, and then what we learn from this is that this muon puzzle is a fine-tuning problem, and we'll have to we have to take good efforts to for precise measurements, but then also to model these measurements with sufficient precision. Okay, yeah, thank you.
Thank you very much, Felix. So now we have much time for question and comments. Anyone have a question? So I have actually the questions. Okay, so the two questions. The first one is about the SIBYLL star. So basically this change is more than the LHC energy. So if we made the muon excess as a function of the cosmic ray energy, so that it should be starting excess from the 10 to 70th electron volt, right?
Uh, okay, this we should maybe study, but not necessarily. It can just be that the showers get small enough below 10 to the 17 that you then don't see the accumulation or this deficit in our experiments, in the air shower experiments, right? Because they get longer and longer, these changes, yeah. So I think it's more like, this is more the scenario than that the interactions at low energies are all correct, right? Because it's not that these high energy interactions are wrong. It's just that they're off all along the way, and in particular also at the lower energies.
Okay, so another question about the not the star in the 2.3D. So you modified about the resonances. So we have the LHF result. We have some constant the eta pi zero ratio. So do you have some comments about this
Yes,
increase in your model?
I
Maybe
was
it's related to resonance.
I was close to preparing a slide on this. Then I didn't. So the thing is, I'm not convinced that that it's really relevant for the air showers, right? Because it doesn't matter if you produce a pi zero or a eta for the shower. So the ratio between the two is true. We will have to retune it for the, and we will for this remnant, right? Because it comes out wrong in the but for the air shower, I think it will not matter because you just have, yeah. The question is if the sum of the two is also off, right? That is the relevant part.
Okay. Okay, please.
Yeah, Felix. One point which I didn't fully understand is this enhancement which you do in SIBYLL star of kaons rows, and then I think that was slide 22. So you can enhance the individual components, but the balance of the individual components, how do you do that? It was the slide 22.
Yeah. 22. Okay. Sorry,
Yeah.
this one.
Yeah, okay. So take that one, yeah.
And the balance between, so it's either, so we either enhance here the row zeros,
yeah,
or antiprotons, not
yeah.
right.
But how you know? I mean, in which way to enhance one over the other?
We don't. We just do one and
Okay.
and see what happens.
Okay.
Or I'm not sure I'm
Yeah,
understanding.
but in the end, I mean, you come to a conclusion and enhance antiprotons, rows, kaons in a certain way.
Well, so we're just enhancing the number of these. Okay, no, we should talk more.
Okay.
I'm not sure I understand.
Yeah, sorry, I was on people.
Okay, so any other question also in the online? No. Okay. Okay, so before the schedule, it's exceptionally we are going fast. So actually, I have one question if we have a time. So you modified again to the SIBYLL star. So you modified the more than the, let's say basically for the more than the energy for the per nuclear regions. But in the final result, the shift, let's say the increase of the mu is mostly constant in the all, let's say the nucleus. Why it happened? Because in the, for example, in the ion, so the part, let's say the per nucleus energy is much lower than the proton. So why it happens commonly in the all nucleus? Do you have any idea?
No, but this is compensated by the fact that this, I mean, the number of muons is not linear in the energy, but energy to some exponent, right? And so if you use superposition, the division of energy doesn't come into play as, I mean, the fact that you distribute the energy among the various nucleons is offset by the fact that you're adding all these showers. And so it's true that the trajectory of each of these showers, so it's less generations, if you like, each of these nucleon subcascades. But it's so the fact that you have more is more important according to the way I don't know how to call it, the Heitler formula is going.
Okay. Okay. Please. Okay.
Hi Felix, thanks very much for your presentation. I'm actually I'm a beginner in the cosmic ray community. I'm very happy to listen to all you guys. So I can see here in that plot you use GeVs and then you plot all the way to 10 to the 5, 10 to the 6. So that's on the PeV region.
Yeah.
Right.
In the center of mass.
Okay. So what I understand is that, well, I heard that there's some experiments such as IceCube that have detected PeV neutrinos, and that's something completely different of what you're showing here. But trying to relate, are you expecting to, is the community expecting to measure cosmic rays in the PeV region or even higher than that? I mean, it's like an open question. Thank you.
This is the other axis, right? So in the center of mass system, it's this energy.
Uh.
But what happens in the atmosphere is you have the atmosphere is at rest and the cosmic rays come in, right? So it's a lab configuration, lab system. So it's this energy. And right, so this is 10 to the 20 electron volt now. So if you like, in your PeV showers, they are here. I think 50, no? 70. 70.
Yeah, between
Yeah,
those. Yeah.
Exactly.
Okay.
So they're seen all the time.
Is the community expecting to see something higher than that? Or not really? I mean,
Cosmic rays?
Is that an event? The 10 to the 20 or
yeah.
this
is
an actual
well,
measurement?
it depends on whose energy scale you believe, but or any of them. But yes, this was measured.
Thank you.
That's why that's why I stopped the plot here. When we measure one at 10 to the 21, we'll have to extend it. Yeah, me too. Me too.
Okay.
Okay, it works.
Okay. I was doing simulation with SIBYLL and looking at distribution, trying to find why the pi0 looks strange yesterday. Actually, I didn't find something for the moment. But I found other things which are interesting. How do you tune your string fragmentation on lab data or on proton data? It's a bit technical, but for example, you have a different PT for pi and k on protons, which is not a prediction of the string model. So how do you do that?
No, it is a prediction if you just change the string model, right? I mean, there's no, it doesn't. So in the default string model, you do this Gaussian, the tunneling basically, which where PT comes from. But no, we're just sampling from a transverse mass distribution, and then this is what you mentioned happens, right? You get different PTs.
Okay, but this is not what we see at lab probably because.
Yeah, sure. We're not tuning to lab because we don't do E plus E minus collisions.
Yeah.
I tried once to just compare a quark string in Pythia that is tuned to a lab and the SIBYLL fragmentation, which is the same in principle algorithm as Pythia, but borrowed a long time ago. And there are some differences, but not so big ones. It's more the differences come more from what we put into the strings.
Okay.
But we tune them with the low energy fixed target hadrons.
Also, you do it like at LHC for the string fragmentation. You do it at SPS and then.
Yes. Well, or in other words, we're now still using the parameters from SIBYLL 2.1, except in the few cases where they were changed. So this was tuned Tevatron at the most, right? Because there was no LHC back then.
Yeah.
And so most of it, I think, is these SPS data now.
No, because agree it works quite well. It's a
yes.
thing. Yeah.
Yes.
Okay. Thanks.
Okay. Okay. Thank you very much, Felix. Again.